Hello guys, how are you doing? I'm here again. Today I'm gonna solve two problems for moment 2D. So let's start. The first problem that I selected is this one, and it says determine the moment about point A of each of the three forces acting on the beam. This is the point A. The point A is located here. And this is 1, 2, and 3 forces. But I'm not going to do that. Instead of doing that, I'm going to calculate the total moment at the point A. That's what I want you to do. Now, first thing that you have to remember is the definition of moment. And as we discussed in the lecture, moment is just a measurement basically of the tendency of a point or of an axis to rotate due to the application of the force. That's basically what is happening. So the object is going to try to rotate with respect to a point or with respect to an axis due to the application of the forces. In other words, if this is the point A and I apply the force, that object is going to try to rotate about the point A due to the application of this force. And that's what we have to do, and this is the way I want you to do. The second thing that I want you to remember is that in order for maximizing the moment and producing the maximum, that's what I'm saying, possible moment, the force has to be perpendicular to the distance. And this is a rule that we always are going to apply when we are dealing with moments in 2D. The third point, define or establish a convention. There is a predetermined convention for a moment that's usually, they say counterclockwise is positive and clockwise is negative, but this is not written in stone. So you can set up your own convention, and you set up your convention by saying something like that. This is positive and this is counterclockwise. Or if you want the clockwise to be positive, feel free to do that, but establish your convention. Once you do that, we're going to start by calculating the summation of the moments at the point A. Summation of the moments at the point A, and I'm gonna use this convention as positive. It's not gonna be other thing that the moment of the force F1 with respect to the point A plus the moment of the force F2 with respect to the point A plus the moment of the force F3 with respect to the point A. And in the case of F2 and F3, those forces have two components, X and Y. So let's start from the beginning. Let's start with the force F3. The F1, I'm sorry. The force F1 says that the value is 375. And as you can see, the force is vertical. Remember what we said in the lecture, and remember this one. The force has to be perpendicular to the distance. So if the force is vertical, I have to measure the distance horizontally from the point A to that force. And that distance is 8, as you can read here. So basically, this is going to be 375, which is vertical, times 8, which is the force horizontal. Now, the next step is to study the direction of the rotation, or the direction of the moment according to our convention. And if you remember, once again, what we discussed during the lecture, I said, imagine that you have this paper, like actually it is not on the board, it is free to rotate, and you're going to set the point A, and you're going to pin, you're going to put a thumbtack, you're going to put a point in that part, and the whole page or the whole figure is going to be able to rotate with respect to the point A, because that's the definition of moment. And then I'm going to apply the force F in this direction because it's acting in this direction. Once I do that, you see what is happening if I keep the point A pressed there. Once again, when I apply this force in this direction, what is happening is this, meaning there is a direction of rotation in this way, and that is clockwise, that is acting in this direction, which is the opposite of my positive convention. Because of that, I'm going to put a negative sign here, because the tendency of rotation or the moment is acting opposite to whatever I define as positive. If I define positive clockwise, this will be positive. Okay, for the case of F2, F2 has two components. It has a vertical component here and a horizontal component here. The vertical component is going to be 4/5, because it's the vertical, this one. 4/5 multiplied by 500, which gives us a vertical component of 400 for that force. And the horizontal component, I'm going to calculate it even if I don't need it later. It's going to be 3/5 times 500, which makes 300. Now let's start with the vertical component. Once again, the force is vertical and the force is 400 multiplied by the horizontal distance, and the horizontal distance between this force and this point A, which is here, the point A actually, the distance is going to be this one, is 8 plus 6 is 14 feet. So then I'm going to multiply that by 14. Once again, you have to study the direction of the rotation for that problem. Once again, I put my point, I put a pin where the whole picture is able to rotate about that point. Later you're going to do this in your mind. You don't have to do it every time, but for the sake of explaining it to you right now, that's why I'm doing it. And then you apply this force here. When you apply that force, the rotation is happening in this way around the point A, and once again, that it's clockwise, which is the opposite of my convention, meaning that it's going to be negative. Now, for the horizontal force, which is here, the force is horizontal. That means that the distance has to be vertical. And if you realize, the vertical distance between the point A and that force is 0, there's no distance. Another way of looking at that is, remember the principle of transmissibility? I'm going to copy it here. Principle of transmissibility. Remember the principle of transmissibility? Basically, it says that you can slide the force anywhere along the line of action, and the effect or the moment that force is going to produce is going to be the same with respect to that point. So I can move that force anywhere along the line of action, meaning that I can put that force exactly there on the point A, because the line of action is horizontal. And if the force is exactly there, the moment produced is going to be 0. So in other words, the horizontal component of that force doesn't produce any moment with respect to the point A. Now let's go to the force 3. Force 3 has vertical component, and this vertical component is going to be 160 multiplied by cosine of 30, because it's adjacent, cosine of 30 degrees. One more time, the force is 160 cosine 30, and it's vertical. The distance then has to be horizontal from the point A, which is here, to the location of any point in the line of action perpendicular, of course, of that force. And this distance is 19 feet. So I'm going to multiply this by 19. Once again, if I pull this in this direction, keeping the point A pin, and I pull it here, that's going to be the direction of rotation in this way, and that direction of rotation, according to my convention, is still negative. Now this force has also a horizontal component acting here, which is the same value that is here, and that force, value component wise, it's not that I can put the force there, the force is applied here. So that force is going to be, because it's the opposite, is going to be 160 times sine of the angle, which is 30 degrees here or here. Or I can say cosine 60 if I want to. So the force is going to be 160 sine 30 degrees. And then the distance has to be, because the force is horizontal, the distance has to be vertical. And I pass a horizontal axis through the point A, and I pass a horizontal axis where the force is, and the distance is this one defined here as 0.5. Now we have to study the direction of the rotation, the direction of the moment, positive or negative, clockwise or counterclockwise. And once again, I put the pin here, and I pull it here. But, you know, it doesn't look like it's going anywhere in that direction, in that way. Then we can apply transmissibility again if you have doubts with that, and you can slide that force anywhere along the line of action. What if I slide the force anywhere along this line of action, and I slide the force to this point, exactly this point? Now I put my pin at the point A, right there, and I'm going to push in this location. When I do that, look what happens. It's clearly seen that the direction of the rotation, or the direction of the moment produced by that force, goes counterclockwise. And counterclockwise, according to my convention, is going to be positive. That might take a little bit of time from you, and even you might think that you know it perfectly. And when you have cases like this, and you have the different legs, like structures in this way, and you want to calculate the moment with respect to this point, or the force that happens here, 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 everywhere around, you always are going to have to apply the principle of transmissibility. Even if you do it in your mind, you have to do it. Now the only thing that I have to do is complete my summation of moments at A. And once I do this times 8, this is 11,000, the negative, 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 positive. The answer is going to be negative 11,192.72. 72 what? What are the units of this? Well, all my units were feet and pounds. So those are going to be the units for the moment. Pound per foot or foot per pound. That's going to be the moment at the point A. Or if you want to, or the problem asks you to do, you can convert this into kip by divided by 1,000. So it's going to be 11,000. In this case, it's going to be 11.19 or 11.2 if you want to, kip feet. Now, this negative sign is really important. That negative sign, what it's telling you is that the moment is going against the positive accepted for me. And if the positive was counterclockwise, negative means that it's going to be clockwise. And that will be your answer for this problem. That's a simple problem, but you have to understand every single part of it, because if you do this and you understood this problem, you shouldn't be having troubles with anything regarding moment in 2D. Okay, let me do another problem for you guys. And this is a problem that I decided to do because every single semester I receive like at least 30 or 40 students that have problems with this particular exercise. It says the tow line exerts a force of 4 kilonewton here at the end of the 20-meter long crane boom. This is the boom that they are referring to, 20 meter long. And now if x equals 25 meter, determine the position theta, this angle, so that this force creates the maximum moment about point O. So what is the moment? We have this distance from here to here, we have this distance, this force applied here, and we have the word maximum moment. I already said it in the previous example, but the maximum moment is always produced when force is perpendicular to the distance, or vice versa. Meaning this angle is 90 degrees, so I already know that. I don't have to do anything else. You guys, that you are the math whizzes and the math whiz, and you like to take derivatives and make derivatives equal to 0, you can do that, and at the end you're gonna realize that that is 0. That is 90 degrees over there. So once I know that, I still don't know my problem. I don't know my angle here, because that angle depends on this and this. By the way, this could be solved just by pure geometry and trigonometry. But I don't want to explain you even that approach, because I can explain it to you. You can make a whole triangle up to this point here, and then call this, I don't know, any way, y or x, and this z, and you know y is 1.25. Then you can say, oh, this total length is at this total length, as this length is at this length, if you want to, or this length is at this height as the other height. There is a way of doing it. You can work it out and you can solve it. But the idea of these type of situations is solving it from the statics analysis point of view. So for that reason, I'm going to calculate the moment at the point O. And the moment at the point O, due to this, and let's do the same convention, positive, like that. The moment is going to be the force, which in this case is 4, multiplied by the distance, which is 20, and is perpendicular. So my moment is going to be 80 units kilonewton meter. Direction of rotation, once again, I put my pin here, and I pull in this direction, meaning the rotation of that force with respect to the point O is going to come in this way, and this way is counterclockwise, because clockwise, and because I say counterclockwise is positive, then this is going to be negative. No problem with that. But I haven't done anything. I need the angle theta. Oh, well, then I can start applying engineering and logic. Remember, we discussed in the previous example, as well as in the lecture in class, the principle of transmissibility. Once again, and per the principle of transmissibility, I can slide any force through the line of action. So what if I decide to slide that force right here? If I slide the force there, I'm going to call this angle phi. And then the component, the vertical component of the force here, it will be 4 multiplied by times sine of phi. And this horizontal component here is going to be 4 multiplied by cosine phi. And look what happened now. What happened now, this is beautiful. What happened now is that I can get the moment with respect to the point O, but now I'm going to use this distance and this distance, because I forget about the top part now, and I say, well, the force is not there, the force is in the bottom part. And because if the force is acting here, I'm going to calculate again the moment at the point O. And the moment at the point O is going to be, let's use the first force, the first component, 4 times sine of the angle, sine of phi, which is this one, multiply, because the force is vertical, I'm going to multiply by the distance, which is 25. And the direction of rotation, once again, I put my pin over there, and I apply the force coming down in this way. I'm pulling it. And that means that it's in this direction, and that direction, according to my convention, is negative. And then this other force is 4 times cosine phi, and the force is horizontal, so the distance has to be vertical between the point A and the force is this vertical distance is 1.5. And if I pull this here, I might have the same trouble, so I'm going to slide the force at this point, and then I'm going to push now here, and I see that the direction is going to come in this way. For this force, it's going to do this, and that is positive according to my convention. And look what we just did right now. We calculated this moment in this way, and we calculated the moment in this other way. But the moment is the moment. It's the same moment with respect to the same point, no matter what. That's the transmissibility principle, of the principle of transmissibility, as you want to call it. So this moment has to be equal to this moment, or this value, negative 4 sine phi multiplied by 25 plus 4 cosine phi multiplied by 1.5 has to be equal to the negative 80 that I had before. And by the way, these units are also the same, kilonewton meter. Once I have this, I can set up an equation by passing this to the other side. This is going to be positive, this is going to be 4 multiplied by negative 1 and divided by 4. I divide everything by 4, and I can get that sine phi, or 25 sine phi, plus 1.5 cosine phi is going to be equal to 20. And this is not plus because I'm multiplying by negative, so this is going to be negative here, negative sign. I'm going to copy it again here. 25 sine phi minus 1.5 cosine phi equal 20. There you go. How many unknowns do I have in this equation? Only one unknown. Are you able to solve that? Well, you should be able to solve that. And even more with the tools that you have, with the calculators that you have. If you have this calculator, which most of you probably have, and this is a non-paid commercial, you can just put that into the calculator, into the equation. There is a function here, and I don't know how to use this calculator very good, okay? But there is a function called solve. So if you go to this, the function is called solve. I don't know if you can see it there. You go to catalog. Let me see. I don't know if the zoom is correct either. So you just take my word for it. There is a word, there is a function here that is called solve. And then you put in parentheses, you put this expression, and you say 25 sine x minus 1.5 cosine x. And then you have to say, I think you have to say also minus 20 equals 0. In some models you can say equal 20, and then you say comma, and say for x, just x, and close the parentheses and hit enter. And this function is going to give you the value for your angle. Be careful though, because you're going to have several values for the angle, even more when these functions are cyclic like that. You can have several values. As a matter of fact, I got here, I don't know, any amount of values. I am negative 4, negative 5.29, etc., etc., etc. But those are negative values for the angle. Remember, we are calculating angles. This is not the one that I'm looking for. So the angle that I got when I do that, I got that x equal, or in our case, phi equal 0.984x34. And then I have bigger angles also, but the angle that we are looking for has to be between 0 and 90 degrees. So that's what I'm taking this angle. And remember, this angle is in radians. So you have to multiply this by 180 and divide by pi. And then you're going to get an angle phi of 56.43 degrees. That's one way of doing it. I don't have any problem with you using this calculator at all. But just be advised that there are some even higher courses that they are not going to allow you to use the titanium calculator or anything like that. So there's another way that you can use a graphic calculator for doing that. And it's, I just said it, by graphing the function. So you come here and then you put the function here and you say y equal 25 sine x minus 1.5 cosine x minus 20 also here. Yes, minus 20 right there. And then you graph the function. Once you graph the function, you get this equation here. If I pass this to this other side, this has to be 0. When I put it like that, right? 0. And that's exactly what I'm going to look for, this 0 here. Wherever the function cuts the x-axis in 0. How do you do that? You can go to math. I think it's F5? I don't know. F5 maybe? Yes. And then you look for 0, enter. And remember, this is working by approximation, so you have to give a previous value and an after value and hit enter, and then you're going to get your value here. And it says xz, which is this value 0.984834, which is the same value that we calculated before and correspond to this angle. Now, what if you don't have even this calculator? What if you have this calculator or something like that? Then you say, well, that's it. I'm done. I can't do it anymore. And you start crying, or you start yelling, or you start screaming, or you just give up. Well, that's not the idea. The idea is not to give up. Why? Because you can still use that calculator. Let's say I'm going to use that calculator for solving the problem. By the way, this is called trial and error, and it's one of the most, even if you don't believe it, it's one of the most powerful methods that you can have for solving equations. A lot of methods, computerized methods, believe it or not, work on trial and error. So trial and error is just that, trial and error. I'm going to get that equation. I'm going to put my equation here in this calculator. And I'm going to assume a first value for this angle. I'm going to say, let's assume that this angle here is 30 degrees, for saying something. And then I'm going to put this equation here. I'm going to put 25 times sine of 30.0. I'm going to put this in parentheses. 30.0 minus 1.5 cosine 30.0 minus 20. And this has to be 0. It's not 0. The value that I get is negative 8.8. Well, let's try with phi equals 60 now and see what value I'm getting. Well, if it's 60, I just have to go here and change my 30 for 60. Here's my thing here, 60. I put a 6 here. I go to the other one and I put 6 here also, and I hit enter or equal, and then I get 0.9. Look what happened. Between 30 and 60, actually I have a 0 crossing because it changed from negative 8 to 0.9. And I know it's closer to 60 than to 30 because of the magnitude of the values. So I'm going to try now with phi equal 50. And as you can see, that doesn't take long. Look at, I'm almost converging now. I have 50 here. And I put 50 here also. Enter. And then I get, for 50, I get negative 1.81. That means that between 60 and 50, I have a 0 crossing again. You see, from negative 1 to this value. So if you want to, you can try a 55 for saying something, because it's in between both of them. 55 degrees. Same thing, you come here again and then change for 55. This is going to take like maybe 6 values. depending on how thorough you want to be, how accurate you want to be the result. And now you get a negative 0.38. You see, we were approaching to this value, to the 0. That means that it's smaller than 55. So then smaller than 55, no, bigger than 55. Because this is smaller, this is bigger. So we can work now with 56. And because it's really close to this value. And then you change again and you put 56. 56. And then you get the negative 0.1. This is almost. And then you can try again, depending on what you want to do. Now, I know the value is 56.4 because I did it before, but even if I don't know it, eventually I'm gonna go to that value because I know I have to increase it a little bit. So if I put here 56.4, which is not the correct value, by the way, because I need another decimal place for that. But let's see what happened with 56.4. Then you get negative 0.00706. Well, this is not 0, but it's almost 0. Then I can increase a little bit this, and I will get the correct value. But I don't need to be that accurate. So 56.4, 56.43, those are basically good results. And you see that the method for trial and error, I don't know if you knew it, but it's good that you practice it because some problems are gonna. I know you're gonna thank me for that in the future, even though you don't take me in person. You're gonna say, "Oh, that's good that I learned that method." Now, but this is not the value that we're looking for. We're looking for this angle alpha here. And how do we get that value alpha if we're looking for zeta? If we are looking for that, if we have the value phi? Well, no big deal, because if this is phi, this is phi also, right? And I know this is 90 degrees, and this is theta, and this is 180. So theta actually has to be 90 degrees minus phi, and theta has to be 33 point. I'm sorry, 33.56. 57 actually degrees. And that's the angle that we're looking for. Practice, please. Keep practicing, keep getting involved with the book, solve more 2D problems. The next lecture, the next exercises that I'm going to do, I'm going to show you some 3D problems now. If you want to try the method that I just described, the previous method that I described, you have something like this here. You know, this is 25, you know, this is 0.75, and you know, this is 20, and you know, this is 90 degrees. Now, you can complete this triangle here and say, for example, this is X and this is Z. So you can relate this with this, and you can get other type of relations here also. You can also say that Z squared plus 0.75 squared has to be equal to X squared. And then I can relate the other one with this one also, and come with a result and get it. But this is geometry, trigonometry wise, and this is a much more engineering wise solution. So guys, then this is only 2 problems for today, or for now. Chapter 2, once again, moment in 2D, and next time it's going to be moment in 3D, and it's going to be resultant of a system of forces and equivalent forces also. See you next time. Have a good day.